of this machine quite easily by just creating this new state, and for every single rule that doesn't exist, just creating an extra one. So this is now a DFA, and this DFA is going to recognize the language generated by this grammar. Okay, unfortunately, I have to go now. Let me stop this. Okay, I'm going to do one more quick example, and then I think this will show mastery of the algorithm for converting regular grammars into finite state machines. The previous video may have cut off a couple seconds early, whatever. Here's a new grammar that's a little bit more complicated. This is, once again, just taken directly from Gossett, and I'm not going to stress too much about the notation, but we have a grammar which consists of some kind of alphabet and a set of non-terminal symbols, a start state, and a set of production rules. Here the alphabet consists of characters A and B. Here we have 3 non-terminal symbols. Here are the rules. How do we convert this grammar into a machine? Well, I think it's basically exactly the same as before. So now I will create, okay, so what do I need to do to outline this machine? I need there to be a set of states. There needs to be an alphabet, so okay, here we set the alphabet of our machine to be equal to the alphabet of the grammar, ignoring the weird stuff with lambda for the moment because I think we've talked that out, and then let the start state of the machine, then I should say that, that the set of states of your machine should be, well, there's going to be a state for every non-terminal symbol, but then possibly more. And that we will let the start state of our machine be the state corresponding to the start symbol of our regular grammar, and what counts as an accept state I will outline in a moment, and this ... indicates that we are going to have to create additional states. Okay, maybe. We begin. Okay, so here I am in state S, which, as promised, I shall make a start state. Now, we see right off the bat that the first rule says that S should go to A, which means that we can generate an A and then terminate the string. Well, we need to create a new state for that, so I will do that right now. Create a new state F, so I'm sort of dynamically or something adding new states as needed, as specified by the algorithm. And it should certainly be the case that from the start state I can read an A and then go to this accept state and accept from that position. But it's also true that I've created, well, I'll just draw them right now. I've created states X and Y corresponding to the other non-terminal symbols of my grammar, and from S I should be able to read an A and go to state X. From X I should be able to read a B and go to Y, and from Y I should be able to read an A and go to the accept state, or read a B and go back. Okay, so this to me is kind of just perfect as is, and here I am going to just stop because I think this is the most honest way to directly translate the production rules of the grammar into the transition rules for the machine. And in some ways we can just ignore Gossett's attempt, as we did in the previous problem, to add in extra kind of black hole states and stuff like that. Here it's going to be more difficult to algorithmically turn this machine into a deterministic finite automaton, given the fact that our grammar gives us a certain amount of choice. In that, you will notice that from the start state, I can either write an A, or generate an A and then terminate, or generate an A and go to non-terminal X. What this means is that this grammar fundamentally gives us some options, And the only really way to translate this into a machine is to allow for some non-determinism here. And because of this fundamental non-determinism in this machine, it's not going to be so easy with a couple of quick little rules to convert this into a DFA, and so I won't even try. So what have we produced here? It's a non-deterministic finite automaton, and that non-determinism is seen in several respects. One is that many states, like S, have no rule for what to do when there's a B. X has no rule for A. F has no rule for A or B. That could be patched up by creating an extra black hole state. But the fact that there are two A's here means that this really is non-deterministic in some kind of way. Well, that's just fine for us because we learned last week how to convert an NFA into a DFA. And so I am done, and I think we've now shown this equivalence quite well, and we shall move on to the second half of the algorithm, which I think is harder, which shows the equivalence of regular expressions and finite state machines. Okay, goodbye.